This video continues a review of quantitative methods in the CFA, and this is reading 10. I'm dividing into two parts. So this is part 1. The next one will be part 2. In this part 1, we'll look at common probability distributions, specifically how we tend to characterize random variables with probability distributions, and we'll be very specific about what we mean by a probability distributions. It needs to meet a certain definition, and we'll look at the important ones, or at least the extremely common ones among a much wider set of possible distributions that we could use. So this is just the tip of the iceberg, but uniform, binomial, normal, and log normal. And these last two, normal and log normal, they go together and are very common with respect to, in the context of, defining stock prices, which is to say, when we talk about daily stock prices, a common first pass is to define the prices as log normally distributed, which is consistent with defining the daily log returns, aka continuously compounded returns, as normally distributed. So that's how these go together in a typical application. Prices log normal, returns normal. I'll explain that in the video, and I look forward to sharing the material. So random variables are huge in finance, and these are the variables whose future is uncertain, although I think this phrase itself is fascinating because in risk we distinguish between, on the one hand, what we call uncertainty, and on the other hand, risk. And there's a difference between the two because the future for all of us to some degree is uncertain, is it not? And uncertainty, therefore, is that blanket sense of not knowing what's going to happen, and we really can't say anything specific or quantifiable about that uncertainty. An example would be if I own Facebook stock, which I do, and if I were to say that I have no idea what's going to happen tomorrow, or the end of next month, or the end of the year with that stock, I really just have no idea. If I were to say it like that with words, it sounds like uncertainty. I don't know what I don't know about it, and I can't itemize the outcomes, and I can't. Therefore, I'm a long way from saying anything quantifiable about that uncertainty, am I not? But our challenge in finance oftentimes is to translate that uncertainty into what we call risk and to characterize it with a random variable. In that case, we actually can make some attempt, even if it's just an attempt, to even just approximate our uncertainty with something quantifiable, specifically a probability distribution. So in that case, I still own Facebook stock, but maybe I would be so bold as to say, well, looked at it historically, and maybe that price follows a log normal distribution. So I still am uncertain about the outcome, but I am saying it's probably going to be somewhere in this distribution. I've characterized the uncertainty with a random variable. And the first distinction there in random variables is between discrete and continuous. Discrete random variables are countable. Continuous random variables are infinite. And I think that's the most helpful way to think about that, which is to say that if we can count the outcomes, then we have a discrete random variable. Here's a graphic we've used before, and then I've graphed here the binomial distribution where probability of success happens to be 0.5 or 50%. And it looks a little bit normal, except that we can actually count. It looks like a normal distribution, except that we can count the number of outcomes here. It's 10. If we can do that, we have a discrete random variable. Here it happens to be binomial, but there are others. And so a discrete random variable can be counted, and examples of that include a coin, a six-sided die. Default on a loan is a good classic example of a default random variable because the loan either defaults or it survives. We have two outcomes. That's a discrete random variable. As opposed to our most famous continuous random variable is plotted here, and that's the bell-shaped curve that we call the normal. So this is a normal probability density function represented here by the continuous line as opposed to the points. And the thing about this, one of the things that's interesting is that we wouldn't say something like the probability would equal exactly 50, for example. We'd have to say, as shown here, what's the probability that the outcome or value is within this interval between two values, because there's an infinite number of values within the interval. So I think the most helpful way to think about this is that a discrete random variable can be counted, 1, 2, 3, 4, 5, as opposed to a continuous random variable actually must be measured because there are an infinite number of values. So examples of that are time, distance, and loss severity. They must be measured. Then we have probability function specifies the probability random variable takes on a specific value. That's interesting to me because that means that a probability function is a special kind of function, right? We might say that y equals f of x, and I have written a function there, and it could be over some domain, that's the x-axis, maybe starting at 0 and going to some constant a, and having some density as follows. That is a valid function, but it's not necessarily a probability function. So probability functions are a special kind of function that meet these two properties. That is to say, the probability of the number of outcome must be between 0 and 100%. When you think about it, that would be true of all the probabilities that you know. We say, what's the probability it's going to rain tomorrow? It needs to be between 0 and 100%. It can't be negative 10%, and it can't be 120%. The probability that it will rain tomorrow, none of those make sense. It needs to be between 0 and 1. And the other is that the sum of all the probabilities needs to equal 1 if we, in the case of the discrete case, if we can itemize those mutually exclusive outcomes, they need to sum to 100. In the continuous case here, for example, that means, as you probably know, that the area under that curve needs to sum to 1.0 100%. So these are the conditions that we would apply to a function that make it special and satisfy a probability function. So, and that is an exam tip as well, because you will see functions that don't meet those, that actually aren't probability functions, and then when we try to do probability math on them, it fails. So we also have, I mentioned that first distinction is between discrete and cumulative, and the other classic distinction, and I'm going to, on the next page, lay these out, but the next big distinction is between the probability density function and a cumulative distribution function. And I can't recall if the CFA syllabus actually did this, but I deliberately put the density function in lowercase PDF and the cumulative distribution function in uppercase CDF. I think that's good practice. It reminds us that the cumulative distribution function is the probability that a random variable is less than or equal to a particular value, hence the term cumulative. So if I represent this visually, these two, when we talk about random variables, these first 2 points that I've so far said are probably the main two ways we carve up this world of random variables. It's this way. Right. Firstly, it's if we look at the columns here on the left, this column refers to a continuous random variable, and this column on the right, you can see, refers to a discrete random variable. And then if we look at the rows, the top row here is the density function, right? So here we have the continuous density function. That would be the lowercase PDF, probability density function, and then its discrete analog here, right? And these are density functions, meaning the area under this curve is 100%, but also summing the area of these bars, we would also get 100%. Here we have the discrete density function. And strictly speaking, and I think the CFA syllabus mentions this in a footnote, but strictly speaking, if we have a discrete density, we would call that a probability mass function. So if you really want to be proper, you could call this a PDF, and this is a PMF, probability mass function, but it's also lowercase. Now, if we just accumulate this, so if we just here were to plot the area here at a given, if we take this 15 as a quantile here, or actually, sorry, why don't I just use the one that's graphed? Here's a 9 or so. That's the quantile. If we go down here, if we just plot the area on the y-axis, then we're plotting the cumulative distribution function. So because this is a probability density function, meeting that criteria, the definition of probability, that means that this plot here by definition must be asymptotic or must converge to 1.0100% here. Capital CDF here is a cumulative distribution function, and it has the same terminology in the case of the discrete. But similarly also here, we're plotting the cumulative area. So when we get here, we're plotting this plus this plus this. So by definition of the probability, as we get here to the right all the way, we need to be at exactly 100% if we have a probability. So that's the two ways to carve up that random variable universe. The discrete uniform distribution is very common, of course. Here, this is discrete because it's the probability that x can equal a value of 1 through 10, the integers. Then the PMF, consequently, probability mass function, if it's uniform, that means that the probability of each outcome is equally likely and therefore 1/10. And cumulatively, then we have a very logical sequence building up to 10 of 10. Bernoulli trial is the building block of the binomial. So a Bernoulli trial only has two outcomes. And so the probability of 1, or this could be success, would be denoted typically by P, and the probability of 0, or we might say failure, might be denoted by 1 minus P. So we only need a single parameter in the binomial distribution. And the assumptions of the binomial distribution, then, we could think of the binomial distribution as it's a series of Bernoullis. However, the thing about the binomial is it's not just any series of Bernoullis. The probability P is constant for all of the trials, and the trials are also independent. So these two collectively together represent a term that you see often in finance textbooks, and that's IID, independent and identically distributed. So the independence here refers to the fact that, well, let's just say I have a coin. That's not a very good coin, but let's say I'm going to flip a coin 3 times in a row. And I ask you, what's the probability that I'm going to get 3 heads? You're probably going to say 0.5 raised to the 3rd power is the probability that I get 3 heads in a row, or 3 tails for that matter. So probability 3 heads. Implicit in our doing that calculation is we're assuming independence, right? When we flip the coin the second time, it doesn't care or know or incorporate any knowledge of what's happened when we flip the coin the first time. The trials are independent, and that's the first I in IID. I think it's the first I. It's one of the I's, independent and identically distributed. Yes, it's the first I. Then the other thing is that the coin has a 0.5 time percentage each time, not like I swapped in some unfair coins such that there's a 0.5 chance of a head, then a 0.3, then a 0.6. If I mixed up some unfair coins, you could actually imagine having different probabilities, but we don't. We have identical or constant for all 3 of the trials. So we say the binomial is the series of Bernoullis, but there's 2 implicit assumptions here collectively in the IID. The Bernoullis have identical or constant P, so there's still only 1 parameter, and the trials are independent. They are not correlated here over sequence or over time. So if we look at the binomial in action, the probability of X successes in N trials is given here by this function. N choose X, then we multiply probability P raised to the X power multiplied by 1 minus P raised to quantity N minus X. So this N choose X is the binomial coefficient. And just to put some color on that, an example here would be, let's say that the probability, we have a binomial, let's imagine a binomial tree, and so that means we're starting here with a stock at 0, and the probability of an up jump is 0.3, and because it's binomial, that means the probability of a down jump is 0.7, so that we'd end up here at SU, or here with 70% probability SD. And you can see in this example, that's just the one step in the binomial. Then we're going to take a second step. So this would be SUU with probability 0.3, with unconditional probability 0.3 squared. And this would be probability of SUD, right, which would correspond with probability of SDU because it recombines. And that's just the second step. So here we're assuming 5 steps in the binomial tree, and the probability of an up jump is 0.3. So we would typically diagram it here. It has a symmetrical look, even though you can see this is a binomial that's not symmetrical. It's going to have skew. In fact, it's going to be skewed here on the downside, but we wouldn't typically visually represent that. So then we've got a table here, but I'll just show you with the calculator. Let me just solve for, how about this line here? See the number here, we are solving for the P of X, and this is a discrete distribution, so this would be the, right here, the probability. It's not labeled, but this would be the probability mass function for the binomial, and then this is the associated CDF, cumulative distribution function, right, because it's the same here at the first outcome, but it's just accumulating, and by definition, it needs to finish here at 100%. So if I just take this row right here, we would like to get the probability that the number of up moves will be 3, right? So that's the what we're solving for is the probability of X equals 3. And actually, if I were going to write this out, the way I would probably write this out in full to be fully informative, I would say, what's the probability that the random variable X equals 3? And I would just say conditional on the parameters, P equals 0.3 or 30%, and N, the number of trials or steps in this case, is 5. And let's see, with a binomial, that's fully specified, so I actually have enough information to solve that with a calculator or software or Excel or R for that matter. So that if I did it with a calculator, okay, so I'm going to use my calculator to solve for the probability of X equals 3. And so here I have the N choose X. So in this case, that's 5 choose 3. And that combination function is right here, but as a second function. So I give it the F5, second, N choose 3 equals, and I get 10. And then I'm going to multiply it by, and I'm just going to put each multiplier in parens to be safe. 0.3, that's my P, raised to the third power, close parens, and then I'm going to multiply it by that final multiplicand. So multiply by, open parens, my 0.7 raised to the second power, close parens, equals on that. I get 0.1323, which is right here. And so that's my probability mass function, probability of X equals 3. So key features of the binomial distribution are the mean and variance. So in the case of a random variable, the Bernoulli, the mean is P and the variance is P multiplied by 1 minus P. And so that's if we have one Bernoulli. But then if we have a series of Bernoullis or n Bernoullis that are independent and identically distributed, so IID, n Bernoullis then each with the same constant probability P of success, the mean is n times P, and the variance is n multiplied by P multiplied by 1 minus P. So for example, if we were asked to estimate the expected number of defaults and standard deviation of defaults in a bond portfolio of 50 bonds, where the default rate of each bond is 12.5%, then the mean that's the expected number of defaults, is simply the 50 multiplied by the 12.5%, so that's the 6.25. Then the variance is 50 multiplied by 12.125 multiplied by 1 minus 0.125, so itself So just to itemize that out, let's see. The variance here is that 5.47 is 50 multiplied by 12.5% multiplied by 1 minus 12.5%, which I suppose is 87.5% or 0.875, and this is 0.125. I meant just the 875 there. So that's the variance is equal to 5.47. Then if I take the square root of that, I get the standard deviation of 2.35, 2.34. And again, that's a distribution of 50 bonds. So we're saying if we do have that portfolio, the expected number of defaults is 6.25, but with a standard deviation of 2.34 defaults. So the continuous uniform distribution, the PDF is represented this way, where f of x is 1 divided by b minus a, and the CDF has this shape here. So for example, a train passes the platform every 10 minutes. What is the probability that the passenger has to wait for more than 7 minutes for the train? We could say that the probability that x is greater than 7 is 3 divided by 10, or 30%. That's if we assume a continuous uniform distribution for this kind of weighting sort of problem. There are distributions that we could use. The normal distribution, obviously very famous and common, and also quite often times justified, especially by the central limit theorem. The normal distribution is convenient or parsimonious because it's completely defined by 2 parameters. That's the neat thing about the normal. We just need the mean and the standard deviation. So much so that in fact that oftentimes in finance, when we're characterizing something like returns, we'll just use the mean and the standard deviation. And implicitly then, if we just stop there with those first 2 moments, we're implicitly assuming a normal distribution because we've only characterized with the first 2 moments. Oftentimes that's the case, or that's the presumption that's made. There are other distributions that we can use, but so common is the normal that oftentimes to present these 2 parameters, mean and standard deviation, is to cause other people to infer that we're assuming normality, or what is sometimes called imposing normality, and sometimes that's not the right thing to do. The normal distribution, related to this fact that it's fully characterized by the first 2 moments, has 0 skewness. That's the third moment function, so it's symmetrical, and it has excess kurtosis of 0. So we would say, this is a little bit tautological, but we'd say a normal distribution has normal tails. What we mean here is these tails are neither heavy nor light, they're neither fat nor skinny. But it's a little bit tautological because it's all relative, is it not? And we just use the normal distribution really as the benchmark here for let's see, no pun intended, but a normal has, by definition, normal tails. So we compare other distributions of the normal, and we say they are heavy-tailed or leptokurtotic if the kurtosis is greater than, if the excess kurtosis is greater than 0. And what we really just mean is that the tail on that distribution is heavier than it is in the normal. Has a really convenient feature here, and that is that the linear combination of 2 or more normal random variables is itself normally distributed. Why is this so convenient? Well, that's because one very common assumption we make about, let's say, daily stock price returns is that, let's say, tomorrow's return, if we divide it by, tomorrow's stock price, if we divide it by today's stock price, And if we take the natural log of that, what I've then done is computed a log return, assuming no dividends, which is a continuously compounded distribution. And then I say it is approximately normally distributed. And so if that, I'm working a little backwards here, but then if I say my daily returns are log returns, or as continuously compounded returns, they are normally distributed, then I have this property, which is technically called time additive property, meaning I can add them together if I've done that, which I couldn't do if I just did a simple arithmetic return. The return over 2 days would be, let's say they were identical, R plus R is 2R, so I can add them together, a very convenient feature. For the normal distribution, we have these rules of thumb. You've probably seen this before. It has its own Wikipedia page, 68, 95, 99 rule, meaning that about 68%, which you'll notice is pretty close to 2/3, falls within one standard deviation in both directions here of the mean. So that what that means is that we could say sort of approximately, if we were given the mean and the standard deviation, we could say that we approximately a little over 2/3 of the outcomes should fall within one standard deviation of the mean. And then if we go out to 2 standard deviations, we'd get 95% of all of the observations, and 3 standard deviations is approximately 99% of the observations. So at that point, then you can see that when we talk about the normal distribution, outcomes or events within 3 standard deviations are very likely. And in fact, observations that are more than 3 standard deviations, especially more than 4 standard deviations, those become the outliers or the rare events. So in terms of the standard deviation, the normal is pretty tight. And then now we have a special case of the normal, right? Because we just looked at the normal, and we would need then to say, if we want to specify that normal, we need to say, what's the mean? What's the standard deviation? If we then say the mean is 0 and the standard deviation is 1, I don't know why I have a 0 there, that should be 1.0, then I've specified the standard normal distribution. And because 1 squared is also 1, the variance is 1 as well. So I've now specified both of the parameters. So the neat thing about a standard normal distribution is that it needs no parameters specified. It's fully baked. I tell you, standard normal distribution, that's all you need to know in order to compute a probability. And of course, famously, we denote it with a z. So even when we use this in code as random variable, I think it's pretty cool to use a z to suggest that it's a standard normal distribution. And I have it down here, the z lookup. And so we would take this transformation here, very common, right? If we have a random variable x, we oftentimes need to standardize it by dividing by the mean and taking that difference, that raw difference, dividing by the standard deviation to standardize it to compute into its standard normal equivalent. And then we can use that as a lookup table or in software. For example, specifically here with the cumulative probability lookup table. And this is telling us here that, for example, if I want, what's the probability that z will be less than or equal to, well, let's just say positive 0.56. It is equal to, if I go to my z table, here's my 0.5, add to my 0.6, it is equal to 0.7123, and I'll put approximately because this is a round number after all. You can see it's a 71.23%, that the probability of that z as a quantile is less than or equal to 0.56, so that's a cumulative distribution function. And if we wanted to just apply that in a problem, here would be a typical sort of very basic exam type question. Consider probability portfolio with a mean of 15% and a standard deviation of 25%. What is the probability that the portfolio return will be between 10 and 20%, assuming that the return follows a normal distribution? So here we can see we've got the assumptions. The mean is 15, the standard deviation is 25%. And I've graphed them here. And what we're really asking here, this graph here is not a standard normal. It's just a normal because its mean is at 0.15, right? For this distribution that's drawn, it's 0.15 with a sigma of 0.25. And then what we're asking for in the problem here is really what's the area in this curve? Probability that z is less than or equal to negative 0.20 is equal to 42%. And for my upper bound, probability that z is less than or equal to positive 0.20 is equal to 58%. And what I've done with both of those is, in terms of my 42%, well, I'll take this out. My 42% is the area here. It is, I used my z, but I'm computing the probability that I will get an outcome here that is less than my lower bound of 10%, and that's the 42%. And then for the upper bound, I'm computing the area under this curve all the way to the second line. That's the probability that my outcome is less than or equal to the 20%. So you can see that if I take the 58%, right, that's all of that area, and subtract this area here to the left of the first line, that difference here, what I'm getting is the area, what I'm getting is the area here. The difference between those two are 15.9%. So that's typical sort of problem that we'd have to do. The multivariate normal specifies the probability of a group of related random variables. Multivariate normal, we need 3 parameters. We need the vector of mean returns on the individual securities. We need the variances of those returns, and we need the distinct pairwise correlations. So, right, if we have, let's say 3 assets, 1, 2, and 3, 1, 2, and 3, right, what we have is a correlation matrix. In the diagonals, we're going to have the variable's correlation with itself. So that correlation matrix will betray itself with 1s in the diagonals, but we need the pairwise correlation, that is the correlation between 1 and 2, between 1 and 3, and between 2 and 3. So we need those 3 values, and because we had 3 securities, right, 3n multiplied by 2, n minus 1 is 2, divided by 2 is 6, divided by 2 is 3. We need 3 pairwise correlations. After all, the correlation of 1 and 2 is the same as between 2 and 1. And so this upper triangle has a mirror reflection, so to speak, in the lower triangle. But that's the curse of dimensionality. As n increases, you can see basically the number of pairwise correlations increases approximately at the square of n. So if we just apply that safety first ratio, here's an example. Portfolio 1, threshold return is 2%. And for the portfolio then, you could see we have this assumption that the portfolio return is normally distributed. So the 2 parameters are expected return is 8% with standard deviation of 10%. Then the safety first ratio of 0.6, well, that is the 8% minus the threshold of 2%. Rewrite that. 8% minus 2%. which itself is 6%, divided by that standard deviation of 10%, equals my safety first ratio of 0.60. And then the probability here, and then I apologize, but this is mislabeled because this should be the, we said it's the probability that the return on the portfolio is less than the threshold, right? So this should be reversed, is 27.4%. And so what we're doing there is this safety first ratio, as you saw, it's really a Z. And so we're anchoring the Z at, let's say, 8%. And the threshold is 2%. And just imagine here a normal distribution centered at the 8, going over here to the 2. So 8% is my mean, and 2% is my threshold. So the numerator, the raw difference here in that Z is 8 to 2. So the raw distance here is 6. But in terms of a Z, dividing by that standard deviation of 10%, it's 0.6. So in computing, computing this probability, we're getting the probability that Z is less than or equal to negative 0.60, because we have the negative in there. What we're really just computing here is in a normal distribution centered on the 8%, what's the probability that we'll be here to the left of the quantile at 2%. So in raw terms, it's less than 2%, but in standardized terms, it's the probability that Z is less than 0.6. So we also have the log normal distribution. A random variable y follows a log normal distribution if its natural log is normally distributed. So the log normal distribution is bounded by 0, and in a related feature, it's skewed to the right, so it's a long right tail. So here I just used some software to plot a log normal with a 0 mean and 1 standard deviation, and also a log normal with a 0 mean also, but a standard deviation of 0.5. So you can see in both cases, bounded by 0 on the left and skewed with a long tail to the right. And so this is very common because I earlier mentioned that probably our most common assumption about returns is that the log normal returns are normally distributed. So we say, right, the natural log of the return, tomorrow's price over today's price, is normal, right? So that's the natural log is normally distributed, and that means that the price itself is log normally distributed. So we say in this simple model, stock or asset prices are log normal, and their log returns are approximately normal. So parameters are the parameters of log normal. We have mean and variance. And then finally, Monte Carlo simulation. So the Monte Carlo simulation uses computer-based techniques to generate a large number of random samples from probability distributions, applications including estimating value at risk and the valuation of complex securities. So we have here, I've itemized the general steps, although if you subscribe to the channel, I'm going to show you, I'll show you shortly in the playlist on the channel, I'll show you some Monte Carlo simulations using software. So I think we have the steps that are in the syllabus, typical for the CFA and also for the FRM, but it's the kind of thing that I think that it's very insufficient understanding of it to just walk through the steps. We actually need to see the Monte Carlo simulation is something you need to see in software. But as terms of general steps, first, we specify the quantities of interest in terms of their underlying variables. So these are sometimes called primitives. So, for example, in this example, we might be using the Monte Carlo simulation to perform a valuation on an exotic option, exotic stock option. In particular, perhaps it's an Asian option, but it could be for any one of the exotic options. Like we could do this for a barrier option to be a good use case for the Monte Carlo simulation. But we're going to value the Asian option. And then one of the first things we want to do is identify those variables, sometimes called the risk factors, that we're actually going to simulate as random variables in the model. And so obvious candidate in this case would be the stock price, right? The stock price itself doesn't give us, knowing the stock price doesn't give us the value of the Asian option, which is a derivative on it, but it's the thing we're going to simulate. In other cases, it's not so easy to identify necessarily what the quantity of interest is, or more realistically, we're going to use multiple variables or primitives that we're going to model. Second, we specify a time grid. That's the phrase in the syllabus. I prefer horizon. We want to split that horizon into a number of subperiods denoted K. So our overall horizon, for example, maybe we're going to model an Asian call option that has a maturity of, let's say, 1 year. I'm going to get a long dated option. That'd be the horizon. And then we need to decide, are we going to model that on a daily basis? So we have 200, maybe K is 250 trading days, right? So that means each step would be, if we're going to, we could be 1 year divided by 250 to determine the time step. We need to specify the distributional assumption of the risk factors. We might have a general model for the stock price here, where it follows some drift plus some random shock. And then we would draw K random variables of each of the risk factors. So here we have this important theoretical step of actually generating a random number, which is a whole topic unto itself. It might be deeper than you'd expect. Not always easy to generate a necessarily random variable. And then if we want to share our results with somebody, we want that to be reproducible. So we need to set a seed so that we generate random variables, but somebody else could recreate our model in order to generate similar results. Number 5, calculate the underlying variables using the random observations. And so in this example of the Asian option, we would use random variables. A random number generator would generate a series of stock prices for us. And then in this step 5, at the end of, let's say, the 1 year, for the purpose of the Asian, we need to calculate the average stock price during the life of the option. 6, then we compute the quantity of interest. So in this case, we've only done a single trial, right? Steps up so far. And so far in these steps, we would take time 0. We've done a random number generator that informed a model of the stock price. We got to the end of the year with that stock price. Right, let's call that S sub 1. That was just the stock price. Then we need to, here in step 6, compute the quantity of interest. That is to say, value the, after we've averaged the stock price, that would inform the value of our Asian option here at the end of the year, but we also then need to discount it to the present value. And that gives us what we might denote here. Here's my discounting. See first trial at the end of the year to first trial discounted back to the beginning of the year, right? So we had a random number, we generated a random number. That random number informed a model for the stock price, but that's the stock price. We needed to average the stock price as part of step 5 to compute the future value of that Asian call option in step 6 and discount it also in step 6 to give us then here what we denote by capital C for the Asian option, which is for that one random trial, we've computed here the present value of the Asian option. And then we go to step 7, which is we go back and do it again for a second trial, a third trial, and on the mini trials, because software is powerful, maybe 100 trials, probably something more like 1,000 trials or more. So that's we iterate back. And then we can, if we have the results of 1,000 trials, you can see we have a vector of 1,000 different present values for that Asian option, we could then generate our statistic, like take an average of it and give us an estimate of its value. That'd be the Monte Carlo simulation in words. But in my own opinion, it's almost impossible to understand just in words. We need to look at software. And so finally, then we contrast the Monte Carlo simulation with the historical simulation. And here, the Monte Carlo simulation analyst chooses the probability distribution, provides statistical estimates, not exact results, and does not provide good insights other than the analytical methods. Versus a historical simulation, this samples from historical returns to simulate a process. It risks which do not occur in the past will not be reflected, and the what-if analysis is not possible as data is a fixed set. So in the historical simulation, rather than this random number generator, we still need a random number to decide which subsample from history we're going to use, but we're sampling from historical returns. Okay, so that's the first part of this reading 10 in this section, and we'll continue in the next video. That'll be part 2 for this topic. If this is helpful so far, please do subscribe to the channel so you're notified of when I in fact do put that video up. Thank you.